Okay, so I put the level of this talk to junior level astronomy students, so I apologize to the experts in the field. It's a talk about the High Altitude Water Cherenkov Gamma Ray Observatory, but to get started, I'm going to spend a good fraction of the time just covering gamma ray astronomy in general, and since I came from particle physics, I like particle physics, so I'm going to talk about the properties of gamma rays and how it's relevant to a gamma ray observatory. Then I'm going to go through an overview of the astrophysical sources of gamma rays, and there are three basic types of gamma ray observatories. I hope to tell you what the differences are. And then I will finally get to a brief description of the TeV.HAWC Gamma Ray Observatory that is currently 2.5% complete. So let's start at the ground floor. What are gamma rays? An arbitrary definition could put the energy at 124 keV or greater. That corresponds to about 10 picometers. Frequencies of 3 times 10 to the 19 hertz. Here's a little cartoon showing the scale of gamma rays, sort of associated with the nucleus. Gamma rays are photons, and as such, couple as photons. They are mediators of the electromagnetic force, which has great relevance to the everyday world, much so than some other particles that I'll briefly mention. They have substantial coupling to matter. It has good ramifications. They're easy to detect. Also, perhaps somewhat detrimental ramifications. They don't propagate very far through matter. The production mechanisms for gamma rays, I've listed 6 major ones. Radioactive decay, electron-positron annihilation, decays of neutral pions, that's of high relevance to astrophysics, electron bremsstrahlung, synchrotron radiation, and something known as inverse Compton scattering. I'm going to describe each of these briefly. Radioactive decay is associated with the rearrangement of the nuclear levels in a nucleus, and the typical energy range is from low keV to mega electron volts. Not so relevant to astrophysical gamma rays, with the exception of maybe supernovas. The other process is electron-positron annihilation, where an electron and its antiparticle combine and produce 2 photons. The energy of these gamma rays is going to depend on the electron and positron energies. The electron and positron masses are about a half a MeV. Another process for producing gamma rays is electron bremsstrahlung. If you take a charged particle and cause it to accelerate, it will radiate away electromagnetic energy as described in your textbook, J.D. Jackson. Again, the energy of these gamma rays depends upon electron and positron energy and momentum. Another process for producing gamma rays is synchrotron radiation of gamma rays. This is mostly relevant for lower energy photons. And I'm going to mention a process where these photons can be boosted up, but the power law for synchrotron emission is shown here. This is out of the 3rd edition of the Jackson textbook that some of you in grad school might be experiencing. The other process for producing higher energy gamma rays is known as inverse Compton scattering. As a joke, I've taken the cover of Time that has Sir Arthur Compton and inverted it. What happens here is that you have a low energy photon scattering with a higher energy electron. The high energy electron transfers some of its energy and produces a high energy gamma ray photon. This is highly relevant in astrophysical processes. Again, the energy scale depends on the scale of the electron energies. Synchrotron self-Compton scattering. So if you're in an environment that has magnetic fields and charged particles, the charged particles spiral along the magnetic fields, give off photons. Those photons can then be upscattered to higher energies by the electrons in that astrophysical system. So here is a spectrum showing synchrotron photons and a second peak at higher energies from the gamma rays. These are multi-wavelength measurements. This is one of the reasons why you hear gamma ray astronomers being interested in doing multi-wavelength measurement observing campaigns with their colleagues at lower energies. So, if you know particle physics very well, and you know the theory of accretion disk, and you understand plasmas, and magnetohydrodynamics, and shocks, you might be able to calculate the spectra of gamma rays from some system that is emitting them. Rather difficult, but it's possible. So, having spent, I don't know how many years here working in this other field, since we're talking about gamma ray spectra, it is somewhat, the spectra of gamma rays is somewhat coupled to cosmic rays because the photo production of pions, the decay of neutral pions producing gamma rays can be related to the proton flux of cosmic rays. So here is what is now called the Hanlon plot, which was the Simon-Sorty plot, showing the flux of cosmic rays. Gamma rays is somewhere down there, depending on where you're looking. The other relevant feature of cosmic rays to gamma ray observatories is that they produce a rather considerable background to the gamma ray events. How do photons, in particular gamma rays, interact with matter? If you go to the Particle Data Group book, they provide you with a very nice plot that shows you the total cross-section for scattering with carbon, in this case. The cross-sectional area, that is basically the effective area of scattering, is measured in a unit called barns. It literally comes from the broadside of a barn. One barn is 10 to the minus 24 square centimeters. Okay? The photoelectric cross-section is considerable at lower energies. 1 megabarn, that's big. Okay? It drops, and at higher energies, the dominant cross-section is associated with pair production, either in the field of a nucleus or of an electron. You should see those components. And even those cross-sections are significant. They're approximately a barn. If you were to listen to a LHC talk, they're talking about picobarns and smaller. To compare gamma rays to this other particle that is sometimes of interest, neutrinos. The neutrino cross-section scattering off of nucleons over the energy range up to 350 GeV is shown here, divided by the energy. But at about 1 GeV of energy, the cross-section of a gamma ray scattering with a carbon nucleus is about 10 to the 14 times greater than that of a neutrino scattering off of a proton or neutron. That's why neutrinos escape from the center of stars and why they're hard to detect. Okay.
How does it compare to protons scattering cross-section? Neutrinos are very weakly interacting particles. What about protons of the same energies?
Protons are in the millibarn, I believe. So it's much higher than protons, but not fantastically higher. Here is a sketch showing the transmission, or actually the opacity of the Earth's atmosphere as a function of wavelength. The reason why I point that out is because the Earth's opacity, the atmosphere opacity, in the range of gamma rays is 100%. So how is it that you can build a gamma ray observatory at 4,100 meters? We'll talk about it.
What's the dominant piece of the atmosphere that's giving you that 100% opacity?
Nitrogen.
Nitrogen?
I thought it was ozone.
Huh?
I thought it was ozone.
For gamma rays? No, it's just, there's a nucleus, the gamma ray creates a shower. I'm going to delve into that. Okay? So direct detection of astrophysical gamma rays requires a little vehicle to lift you above the Earth's atmosphere. However, the gamma rays don't penetrate the atmosphere, but the secondary particles from the showers that they produce can go to lower altitudes, but it's better to build your detector at 4,100 meters on a Mexican volcano. The other way of detecting gamma rays is to look at the Cerenkov light emitted by the charged particles in the secondary shower. So just for kicks and giggles, I put in here the density and pressure of the Earth's atmosphere. The density is relevant for figuring out how air showers are going to develop. Here was an interesting little plot showing the breakdown of the sources of opacity for visible light. Okay, so the Earth's atmosphere prevents the gamma rays from reaching the surface. However, the gamma rays will interact with a nucleus in the upper atmosphere and initiate what's called an extensive air shower. Here is a plot from the particle data group that shows an electromagnetic shower not in the atmosphere but in some material such as tungsten or lead. I don't know what this one's for, but after about 7 what are called radiation links, you have a maximum number of shower particles created. Depending on the energy and depending on the energy, that number increases. So if you can measure the number of shower particles at the maximum, you can get an estimate of energy. This is what's done by our colleagues doing ultra-energy cosmic rays. These showers are produced by gammas. They're also produced by protons. Here is the results of a simulation of gamma ray air showers for various energies. And you can see that the more energetic the shower is, the deeper it penetrates. Okay. Since many of the gamma ray observatories, in particular Veritas, use Cerenkov radiation to actually observe these air showers produced by the gammas, I had to mention what Cerenkov radiation is. It's radiation that's emitted by charged particles that exceed the speed of light in a medium. The speed of light is 3 times 10 to the 8 meters per second divided by the index of refraction. Charged particles can exceed that speed. And when they do, like a sonic boom, they produce not sound, but light. This is Cherenkov radiation from a nuclear reactor. Okay. The gamma ray, quote, window results from the fact that the gamma ray itself doesn't penetrate to the surface of the Earth, but the air shower that it generates can reach the surface of the Earth. Actually, this is photoshopped imagery. This shower is actually PowerPointed imagery. This air shower is for a 2 TeV gamma ray. This detector located at 4,100 meters actually would be sampling it somewhere up here where there's a significant number. So PowerPoint drawings can be misleading. Okay. If you're using an imaging air Cherenkov telescope, such as this cartoon illustrates here, the telescopes observe the Cerenkov light that's produced by these charged particles in the shower. I believe Stefan gave a talk about Veritas a little while ago. So let's talk a little bit more about the gamma ray air shower. Here is a nice cartoon produced by the Max Planck Institute in Heidelberg, showing an incoming gamma ray interacting with a nucleus through pair production. So you can't spontaneously produce the electron and positron. You have to be in the vicinity of some electrically charged object such as a nucleus. Those electrons and positrons then further interact with nuclei in the atmosphere through bremsstrahlung. So here you have a charged particle going through a region of electric field. It gets accelerated, emits a photon. Then these photons pair produce yet again, and on and on and on. So you have an energetic photon, say 100 TeV. It can produce a significant number of charged particles through this process.
Is the distribution of places where these showers take place, sort of, if I look, sidelong at the atmosphere, do they all sort of take place at the same altitude, or is there a big distribution, or is it
Throughout.
Exponential increase, exponential decay.
Sure, that's the nature. I would imagine that's true, but then it's a question of how big is the
So here's an even more misleading cartoon that shows how you can estimate the number of charged particles. The shower keeps going until basically you can no longer pair produce. Once the photon doesn't have more than 2 times 0.511 MeV of energy, it cannot produce photons. And then the shower starts to go down. The longitudinal development of the shower is expressed by this relationship here. It's basically a curve that goes up, and then down. You've seen it many times in the cosmic ray talks.
We have a quick question. Does Xmax correspond to where pair production stops?
No. No. It's where the maximum number of shower particles occurs.
Wayne, how can you tell whether the shower is induced by gamma ray or by proton?
That's the difficulty. How clumpy the showers are when they hit the ground.
How what?
Clumpy. We'll talk a little bit more about it. Basically, in a hadronic shower, you can have a pion travel further away and create a neutrino and a muon, and these showers are broader
Okay.
and they're not as smooth laterally.
So
It's a very, that's
you need to detect the spread.
right, and how clumpy it is.
Okay.
You'll see later.
I'm looking forward for lumpiness.
Okay, so that was a discussion of the basic physics of gamma rays related to gamma ray astronomy in 27 minutes. That's pretty good. Now getting more into astronomy in general, I wanted to point out some differences between standard astronomy and gamma ray astronomy. So I'm going to do that. Then I'm going to talk about the gamma ray detectors themselves, and then talk about some potential astrophysical sources of the gamma rays, as well as some interesting things like gamma rays being produced by dark matter annihilation. Also, gamma rays might be useful for identifying regions where you have cosmic ray acceleration. And you can distinguish that from other processes by measuring the spectra of the gamma rays. And then a brief mention of the fact that you can't see to the edge of the universe in gamma rays because they don't propagate all the way across. So, a little cute comparison to optical astronomy. So the thing that's great about astronomy as compared to cosmic ray physics is that photons point back to the sources. You can actually see things in the sky. For very high energy cosmic rays, that's also potentially true. But for lower energy cosmic rays, the magnetic fields scramble things up, and even if you measure the direction of the cosmic ray isn't necessarily pointing back to its source. For ordinary astronomy and extraordinary astronomy, the photons, be it visible light or gamma rays, point back to the sources. This is way cool, especially coming from cosmic ray physics. So the other thing that astronomers do is they measure the intensity of radiation versus wavelength or energy or frequency. And most of what I call ordinary astronomy is related to thermal processes, such as stars that are closely approximated by black body radiation. Shown here is an example of the spectrum of the sun compared to black body radiation. Extraordinary astronomy, the sources have somewhat more interesting spectra, like this double hump. This is indicative of non-thermal processes, relativistic processes. Another little cute contrast between ordinary astronomy and extraordinary astronomy is the observatories themselves. So in optical astronomy, you have some really clever guys who figured out a way to efficiently collect the information by making telescopes that could be large and collect the photons and focus them onto a small area. So you could have a really nice detector that's small, coupled to optics that gives you a big light bucket to collect more light while keeping your detector expenses as low as you possibly can. So you have a larger aperture and smaller detector. For gamma ray astronomy, for the satellite-based and the surface arrays, the aperture of your detector is equal to the sensitive detector area. So if you were using CCDs to build surface detector arrays, you would need a lot of money. Okay? So that's why we do some clever things with big buckets of water. The upside to this somewhat negative feature is that these detectors have a wide field of view compared to, this is an artist's conception of the 30-meter telescope, which is supposed to have a field of view of 20 arc minutes. This detector, which is about 150 meters across, has about 120-degree field of view. It's limited by the fact that gamma rays coming in at very high zenith angles aren't going to reach the detector. But the imaging is still done, because when the showers arrive on the ground, the shower plane hits the detectors at different times. And by looking at that timing information, you can still have angular resolutions of less than about a degree. It's not like astronomy, not 0.6 arc seconds, but you can still image the sky. Okay? So what can you study with gamma rays? Here's some broad categories. Compact objects and their relativistic outflows. I'm going to go through a list of those. Perhaps the origin and propagation of galactic cosmic rays, because where cosmic rays are being accelerated, you're probably producing gammas as well. Dark matter. If dark matter annihilates, it's likely that in some scenarios you're going to produce regular particles, gamma rays. In some scenarios not. Another thing that you can study is the extragalactic background light by looking at how the gamma ray sources are attenuated. I really didn't go into this, but fundamental physics such as testing the structure of space-time can also be done by looking at the time arrival of the higher energy gamma rays. I'm not going to really go into that.
So when, speaking of dark matter, how can you know whether it was a dark matter particle or a normal particle that produced gamma rays?
If you had like annihilation of a particle and a particle, you might have a line. So that would be a real smoking gun. You would see a peak
A peak in frequency?
in energy, yeah.
Energy?
Yeah.
A line would be a smoking gun. You're probably not going to see that.
But
So
you
you
detect
could
a shower.
you could look at the whole spectrum and see if it matches
No, but
one of the known sources. Or
you measure properties of the shower to estimate the energy of the incoming gamma with some degraded resolution. So seeing a peak is difficult.
So the dark matter particle for this to be possible needs to have a very different mass, right? From whatever is emitting from a nucleus, for example.
Right,
From a
right,
proton.
right. And more than likely, it's not going to give you a single line. So
I'd just like to point out that many of my esteemed colleagues have stood in your spot and tried to explain to me that dark matter, we don't really know what it is or what it's made of, and now you're going to tell me that we figured out how it goes away.
no, I haven't. No, I haven't. I said there's a possibility that when it does go away, it can produce a gamma ray.
We'll know that. Even though we don't know what it is.
Not necessarily. It needs to have a sufficiently high flux that we can measure it above the backgrounds.
Would this put constraints on dark matter models?
yeah, absolutely. So you know by mass how much dark matter there is around, say, a galaxy cluster, because you see the motions of the objects in the cluster of galaxies, right? And if that dark matter is some particle that annihilates, there are lots of particle physics models for that, then you would expect some signal. If you don't see any signal, then
upper,
It's detecting gamma ray signals from some object that would not normally produce gamma rays through.
right, right,
Like dwarf galaxies.
right, exactly, right. You're Andy's an expert. I'm just a neophyte. So, so where was I? Active galactic nuclei, gamma ray bursts, both short duration, long duration. Objects known as pulsar wind nebula, starburst galaxies, supernova remnants, pulsars, solar flares even, as well as this diffuse emission, dark matter, and the sources of ultra-energy cosmic ray acceleration. I'm going to go through some of these, one slide at a time. So, the textbook Carroll and Osley, which I use for Introduction to Astrophysics, even has this sketch of the unified model of active galactic nuclei. And basically it consists of a black hole surrounded by an accretion disk. The infalling matter creates jets. And in those regions, very interesting things happen that I'm not going to pretend to understand whatsoever. Shock waves of various sorts accelerate the particles, and you produce high energy protons, high energy gamma rays, and depending on which way you're looking, if you're looking right down the barrel, you're looking at what's called a blazar. If you're looking off to the side, you're looking at various different objects, Seyfert galaxies. The spectra that one might expect from such a relativistic process is sketched here, showing intensity, flux versus log of the frequency. There, for radio loud objects, you have signal from radio. Radio quiet, not much signal from radio. Then there's emission up into the gamma rays. Okay? So that is a real cartoonish description of active galactic nuclei. But there are places that can produce gamma rays that should be visible. The other objects are gamma ray burst, long duration and short duration. The long duration gamma ray burst is believed to be something associated with a hypernova, a collapsing star. Short gamma ray burst, one model is the collision of two neutron stars. Both of those produce bursts of gamma rays. Here's a nice cartoon from NASA illustrating neutron stars colliding with some complexities of jet-like magnetic fields. And here's a nice little interlude from that provided by NASA of a movie showing an artist's conception of a neutron star collision. Here it comes. So we have two neutron stars, they coalesce, and then physics breaks down and you get lots of gamma rays. These long duration gamma ray bursts are believed to be associated with peculiar supernova explosions of supermassive stars. Presumably they're associated with type 1b or c supernova that lack or possess hydrogen lines. I can never keep that straight. Lack hydrogen.
But they're massive supernova.
Another astrophysical object that can produce gamma rays is known as the pulsar wind nebula. Here is an image that was the astronomy picture of the day. I can't remember the date. Showing the pulsar wind nebula associated with the crab. The crab is a very useful object that I'll point out a couple times. Here is a cartoon depicting the pulsar wind nebula, again, it's associated with some object that has accretion disk and jets, and out in this region you have acceleration of charged particles through some mechanism unbeknownst to me and unbeknownst to, I think, most people, perhaps everyone. In this region you can produce gamma rays, and the spectra of the gamma rays exhibit this double hump feature. Again, it's useful to do multi-wavelength observing campaigns to study such objects. Starburst galaxies have also been shown to produce gamma rays. Here is an image from Veritas and the spectra associated with the galaxy M82. Supernova remnants also have been associated with gamma ray production. Here is the observation by the HESS collaboration of Cassiopeia A supernova, as well as a spectral measurement, both by Kangaroo and HESS. And then another brief interlude, the really cool video, again provided by NASA, showing an artist rendition of a pulsar interacting with a red giant, forming an accretion disk. And again, in such relativistic regimes, you have the production of high energy particles, which then also produce gamma rays that can be observed and studied. Just go to the NASA website. They have really good artists at NASA. One of the topics that gamma ray astronomy is studying is, are gamma rays associated with ultra energy cosmic rays? There have been some papers reporting that there's been some observations of gamma rays associated with the production of cosmic rays. Modeling of that has been done as well. Okay, so those were the potential sources of gamma rays. There are many. They come from isolated spots on the sky. They're associated with known and sometimes unknown objects. Coupling observations with lower energy observatories provide a fuller understanding of what's going on in those objects. Another thing that can be done with the gamma rays is using them as a probe of intervening medium and measure the amount of basically lower energy photons by noting how an observed spectrum differs from what you expect. And you can study this extragalactic background light. The other thing to point out is that you cannot see forever in gamma rays. Here are some simulations with assumed levels of background light indicating that for various energies, so for various distances, you can see energies only to certain levels. So for objects at Z redshift 3, you would only expect to see gammas with energies up to 10 GeV. That means HAWC will not be able to see anything at redshift 3 because a 10 GeV gamma ray is not going to make it to ground level at 4,100 meters. For Z equals 1, it's expected that gamma ray energies up to 100 GeV can be seen. Again, that's a model depending upon the amount of extragalactic background light. Another plot that I should have removed. Okay. Now, finally, we're not yet to HAWC. Actually, this is an old rendition of HAWC. A comparison of the observation techniques. So imagine you have a gamma ray incident on the planet Earth. In the Earth's atmosphere, it's going to produce an electromagnetic shower. Above the Earth's atmosphere, you can put a satellite. I should have made it as big as the WMAP satellite, but on the plot that they had. The downside for the satellite-based observatories is that they're small, only about a square meter in area. The flux falls off, so the sensitivity of the satellite-based observatories is limited to lower energies. On the ground, if you're clever, like Stefan and Dave, you build... Huh? What was that? You build a large mirror that can collect Cherenkov photons. And you can observe the air showers above you. The showers do not have to hit the ground. The charged particles will produce Cerenkov photons that can reach you. So this should enable you to go to lower energies than a ground-based array. It also has the benefit of having a larger aperture. The Cerenkov photons are spread away from the shower itself, so you can effectively have a larger collection area using imaging air Cerenkov detectors. The HAWC observatory is a surface detector array, which I'm going to describe in more detail. Those require the charged particles to hit the ground. So if you have a 1 GeV photon incident, there's no way you're going to have a sufficient number of charged particles hitting the ground. At 4,100 meters, we expect to have some of the 50 GeV showers having a few particles hit the ground if they're coming vertically through the atmosphere. If you're looking at larger zenith angles, you're looking through more depth. So as you go to higher zenith angles, your sensitivity in energy has to go up. The required energy goes up for higher zenith angles. Okay? So there are three general categories of gamma ray observatories illustrated on that slide. And I continue a description of those three different techniques. The satellite-based particle physics detector, like Fermi glass, is basically a little particle physics experiment flown on a satellite. Intrinsically, they're going to be small, so they have a small aperture. They do have a wide field of view. They are sensitive to particles coming in basically all directions. The Earth sort of blocks a good part of their field of view, though. So more than about half the sky is visible. These are, I don't know, background free. I don't think anything's background free, but their propaganda said that. They have high duty cycle. They have a high duty cycle in that compared to air Cherenkov telescopes that can only operate when it's dark, these can operate basically all of the time. Given about $100 million worth of particle physics technology, you can achieve pretty high resolution in measurement of energy and directions. Because of the small areas, they have low sensitivity to higher energies where the flux is less. The air Cherenkov telescopes have a large effective area because they can see showers that don't directly hit them. They pick up the Cerenkov light. They have to be a few degrees away because the Cerenkov radiation is beamed. They do have a narrow field of view. So like optical astronomy, the air Cherenkov detectors are pointing to and sensitive to a relatively small region of the sky. What's this area of Veritas?
It's going to be nice to use a picture of Veritas instead of a picture of our competitor.
Yeah, I have a slide for Veritas. They have excellent background rejection. The duty cycle, that is the fraction of time they're operating, is affected by things like the sun and the moon. They have high resolution in measuring energy and angle, and they are sensitive to slightly higher energies than the satellite-based detectors. They have good angular resolution, so they can actually study the morphology, the structure, the spatial structure of some of these objects. They have good energy resolution, so they can measure spectra well. They're not looking at the whole sky all the time. So you're basically doing a survey of various interesting regions of the sky. A surface detector array such as TeV.HAWC or Milagro has a moderate area because it's basically restricted to the size of your detector. It has a wide field of view in that it can observe showers coming in up to like zenith angles of 60 degrees, so a good fraction of half the sky. It has a high duty cycle. You can run it during the day. It has not quite as good energy and angular resolution as air Cerenkov detectors, but good enough to do physics. And it has higher sensitivity at the highest energies compared to the other techniques. The other thing that's very interesting about these surface detector arrays is that they're sensitive to the whole sky. So if there's something that pops off somewhere, it's not just luck that you're looking in that direction. You're basically doing an all-sky survey restricted to the latitude of the detector all the time. It also has sensitivity to sources that have a large angular extent on the sky. Okay. So a little bit of history. I was 1 year and 10 months old when the first gamma ray observatory, or gamma ray detector probably is a better term, was put into operation. The Explorer 11 experiment. It was a rather simple device. It had a spark chamber, and it had scintillators for vetoing charged particles, and it was sensitive to the electron-positron produced when a gamma ray entered its sensitive volume. Here's a really cute plot. Those of you in cosmic ray physics will really appreciate this. Here is an aperture, effective detector area versus energy. The telescope array has effective areas of 10,000 square kilometers, just a little bit less than that. This detector had an aperture of 8 square centimeters. I really like that. It did get some results, mostly upper limits of gamma ray fluxes from these various objects. I really don't know how to read that result table, but there was quite a bit of activity in gamma ray observations, starting with this Explorer 11 on various satellites and other missions such as Apollo. Gamma ray detectors were flown, quite a number. This was up through 1973. The duration of the operation, yes. Another interesting historical tidbit associated with gamma ray astronomy is the VELA program that was initiated by, I guess, President Kennedy when he signed a nuclear test ban treaty with Russia and commissioned DARPA, it's actually called ARPA, to verify that tests were not being done. So these Vela satellites were looking for gamma rays, not from astrophysical sources, but from thermonuclear explosions conducted on the surface of the Earth. And in 1973, several years after observations were made, they declassified the results showing gamma ray burst. There were subsequent missions such as the Compton Gamma Ray Observatory with various detector elements like EGRET, COMTEL, and BATSI that observed gamma ray burst. This plot shows that the gamma ray bursts were not confined to the Milky Way, but basically in all directions of the sky, hence probably extragalactic in nature. I will skip that slide. The latest and greatest satellite-based gamma ray observatory is GLAST, which has subsequently been renamed Fermi since it didn't blow up on launch. It's basically a particle physics experiment in a box at altitude. And some interesting results, most recently on March 7, 2012. Something interesting happened to the nearest astrophysical object of consequence. There was a solar flare. On March 6th, this is what the Fermi view of the gamma ray universe looked like. On March 7th, the brightest object was the sun. So the sun also can sometimes be a source of gamma rays. Another interesting result from Fermi is these bubbles showing a much better view through the mind of an artist is shown here. So this is somewhat reminiscent of these interesting objects with accretion disk and jets. It's our own galaxy. Another little video showing the gamma ray sky seen by Fermi. And then here's Stefan's detector, Veritas, whole list of science topics. It's been very productive. Milagro, the predecessor to TeV.HAWC, which basically proved the capability of the ability to distinguish gamma rays from the proton background using water Cherenkov detectors. The TeV.HAWC collaboration, recently grown with Aaron and Andy. And then finally, when I'm running out of time, at this brief discussion of TeV.HAWC, showing the sensitivity as a function of energy compared to its predecessor Milagro, the Whipple, Hess, and Veritas. You see that TeV.HAWC has sensitivity to higher energies. Let me quickly go through some of the science goals. I've already talked about the science goals of gamma ray astronomy in general, but TeV.HAWC in particular is interested in looking at particle acceleration in astrophysical jets, using scalar readouts, which I'm not going to get into detail. There's some sensitivity to gamma ray burst, so it can be used as a gamma ray burst detector. It has the capability of measuring energy and hence a spectra out to 100 TeV. One of its goals is to map the diffuse gamma ray emission. Given the wide field of view, it's sensitive to basically diffuse emission over the whole sky. It also is going to be used for studying cosmic rays, given that 99.99% of the events are cosmic rays. We're going to look for anisotropies. It's going to be used for studying new physics and exotic phenomena, dark matter annihilation, Study the spectra of distant AGNs, even doing fundamental physics studies by looking at the arrival times and energy correlations. It can also do solar physics. The task is to do an unbiased sky survey over a good fraction of 2 pi steradians. We should be able to detect a 50 millicrab source, that is a source that is 1/20th the flux of the crab pulsar in a single year. Again, looking for extended sources of TeV gamma rays, measuring spectra, and looking for things that go bump in the night. I think I'll just stop there.